Galaxies are not static, unchanging entities, they are cosmic masterpieces in motion, constantly evolving over billions of years. Think of them as celestial artists, painting the universe with stars, gas, and dark matter, creating a dynamic tapestry that stretches across the cosmos. But here's the mind-bending part. Just like living organisms, galaxies are born, grow, collide, and even die, their transformations shaping the very fabric of existence. How do these cosmic giants change over time? And what can their evolution tell us about the origins of life itself? In this journey, we'll uncover the secrets of galactic birth, explore the dramatic collisions that reshape entire star systems, and even peer into the mysterious deaths that mark the end of a galaxy's story. Together, we'll unravel how these galactic transformations influence the universe on the grandest scale, revealing a narrative that's as awe-inspiring as it is profound. Ready to dive into the art of cosmic evolution? Let's begin. In the beginning, the universe was a swirling cauldron of chaos, a seething expanse of energy and particles left in the wake of the Big Bang. Picture this, a vast, featureless void, dark and silent, yet brimming with potential. Then, something extraordinary happened. Tiny ripples in the fabric of space, time-imperceptible fluctuations in density began to grow, like seeds planted in the cosmic soil. These subtle variations, no more than faint whispers in the early universe, set the stage for the birth of the very first galaxies. Gravity, the great sculptor of the cosmos, went to work. Dark matter, an invisible yet powerful force, wove an intricate web across the universe, creating gravitational wells that drew gas and dust into their embrace. Within these deepening pockets of gravity, the first stars ignited, their light piercing the darkness of the cosmic dawn. It was a moment of transformation. A universe once cloaked in shadow began to shimmer with the glow of newborn stars. These early galaxies were nothing like the majestic spirals or glowing ellipticals we see today. They were small, irregular, and chaotic, bursting with the raw energy of creation. Yet they were the building blocks of everything we know. From these humble beginnings, the universe began to take shape, setting the foundation for the grand structures we observe billions of years later. And as these infant galaxies grew, their stories of evolution would only become more fascinating. But how did they transition from these chaotic beginnings into the orderly, awe-inspiring systems we see today? That's where the next chapter of their journey begins. As galaxies began to take shape in the early universe, there was an invisible force at work, one that couldn't be seen, but whose presence was undeniable. This force is dark matter, the hidden scaffolding that holds the cosmos together. Imagine the roots of a massive tree, unseen beneath the soil, yet supporting the towering structure above. In much the same way, dark matter provides the gravitational framework that allows galaxies to form, grow, and evolve. Without it, the universe, as we know it, would simply fall apart. So, what exactly is dark matter? Unlike the stars, gas, and dust we can observe, dark matter doesn't emit, absorb, or reflect light. It's entirely invisible to our telescopes, yet its gravitational pull is unmistakable. Scientists first began to suspect its existence when they noticed something strange about the way galaxies rotate. According to the laws of physics, stars on the outer edges of a galaxy should move slower than those closer to the center. But observations revealed the opposite. Stars at the edges were moving just as fast, if not faster. This could only mean one thing: there had to be more mass in the galaxy than what was visible. That missing mass, dark matter, another piece of evidence comes from gravitational lensing. a phenomenon where the gravity of a massive object, like a galaxy cluster, bends the light from objects behind it. Sometimes, the amount of bending is far greater than what the visible matter in the cluster can account for. Again, dark matter steps in to explain the discrepancy. It's as if the universe is giving us clues, pointing to this mysterious substance that shapes everything around us. Dark matter doesn't just exist in isolated pockets, it forms vast, interconnected networks called cosmic webs. These webs act like highways, guiding the flow of gas and dust into the gravitational wells where galaxies form. Over time, galaxies grow by pulling in material from these dark matter filaments, their evolution tightly intertwined with the invisible structures surrounding them. But dark matter's role doesn't end there. It also acts as a cosmic glue, holding galaxies together even as they spin at incredible speeds. Without this unseen anchor, galaxies would fling themselves apart, their stars scattering into the void. It's a delicate balance, one that highlights just how crucial dark matter is to the story of galactic evolution. As we peel back the layers of this cosmic mystery, we begin to see how dark matter and galaxies are partners in a dance that has lasted billions of years. Together, they create the intricate structures we observe today, from spiraling galaxies to massive clusters that stretch across the universe. But what happens when galaxies collide, or when their dark matter halos interact? That's where the story takes an even more dramatic turn. Deep within the heart of galaxies, where clouds of gas and dust swirl in vast, cosmic rivers, the life cycle of stars begins. These stellar nurseries, like the Orion Nebula, are some of the most breathtaking regions in the universe, places where raw materials come together to ignite the fires of new stars. Picture a dense cloud of hydrogen gas, slowly collapsing under its own gravity. As it contracts, the pressure and temperature at its core rise until finally, nuclear fusion ignites. A star is born, lighting up the darkness with its radiance. But stars aren't just born, they live, they age, and they die, their lives playing out on scales that defy human comprehension. Take our Sun, for example. It's a middle-aged star, quietly burning hydrogen into helium for billions of years. But not all stars are so stable. Massive stars, many times heavier than our Sun, burn brighter and faster, their lives a fiery sprint rather than a marathon. These giants blaze through their fuel in just millions of years, ending their lives in spectacular explosions known as supernova. When a supernova occurs, it's like a cosmic fireworks display on an unimaginable scale. The star's outer layers are blasted into space, scattering heavy elements like iron, gold, and uranium across the galaxy. These elements, forged in the heart of the dying star, become the building blocks for new stars, planets, and even life itself. Without supernova, the universe would be a much simpler place, devoid of the rich diversity of elements that make up everything from the ground beneath our feet to the blood in our veins. The Orion Nebula offers a stunning example of this process in action. Located just 1,500 light-years from Earth, it's a bustling stellar nursery where hundreds of stars are being born. The nebula's glowing gas and dust are illuminated by the light of young stars, their energy sculpting the surrounding material into intricate shapes. Over time, these stars will grow, evolve, and eventually die, their remains enriching the galaxy with the raw materials for future generations of stars and planets. This cycle of birth, life, and death is more than just a cosmic spectacle, it's a driving force behind the evolution of galaxies. As stars form and die, they shape their surroundings, influencing the structure and composition of their host galaxies. Supernova, for instance, can trigger the formation of new stars by compressing nearby gas clouds, creating a ripple effect that spreads across the galaxy. At the same time, the heavy elements they produce enable the formation of rocky planets and the complex chemistry that makes life possible. In this way, stars are both the architects and the storytellers of their galaxies. Their lives leave an indelible mark on the cosmos, weaving a narrative of creation, destruction, and renewal that spans billions of years. And as we look out at the night sky, we're not just seeing points of light. We're witnessing the ongoing story of cosmic evolution written in the lives of stars. But what happens when galaxies themselves collide, their stars and gas clouds thrown into chaos? That's where the story takes an even more dramatic turn. Galactic collisions are among the most spectacular events in the universe, a cosmic dance where entire galaxies, each containing billions of stars, spiral toward one another in a gravitational embrace. Unlike the violent crashes we might imagine, these encounters unfold over hundreds of millions of years, a slow-motion ballet of stars, gas, and dark matter. Far from being destructive, these collisions are transformative, reshaping galaxies and sparking new waves of star formation in their wake. Take, for instance, the future collision between our Milky Way and the Andromeda galaxy. Right now, Andromeda is hurtling toward us at about 250,000 miles per hour. But don't worry, this cosmic meeting is still roughly 4 billion years away. When it finally happens, the two galaxies will begin a mesmerizing dance, their stars and gas clouds swirling together in a chaotic yet beautiful display. What's fascinating is that, despite the sheer number of stars involved, actual collisions between stars are incredibly rare. Galaxies are mostly empty space, so stars will simply pass by one another, their paths altered by gravity, but their structures largely intact. What truly changes during these mergers is the gas. As the galaxies draw closer, their vast clouds of hydrogen gas collide, compressing and heating up. This triggers bursts of star formation, lighting up the galaxies with newborn stars. Imagine thousands of stellar nurseries igniting all at once, their brilliance illuminating the darkness of space. These starbursts are some of the most intense and luminous events in the universe, turning what was once a serene galaxy into a dazzling spectacle of cosmic rebirth. Galactic collisions also reshape the galaxies themselves. The Milky Way and Andromeda, both spiral galaxies, will eventually merge to form a single elliptical galaxy, a smooth, football-shaped collection of stars with no distinct spiral arms. This transformation isn't just about appearance, it's a fundamental shift in the galaxy's structure and behavior. The chaotic orbits of stars in the merging galaxies settle into more stable paths, creating a new, unified system. But the effects of these collisions don't end there. The gravitational interactions can fling stars and gas out into the void, creating long, luminous streams known as tidal tails. These tails are like cosmic brushstrokes, painting the aftermath of the merger across the universe. And in some cases, the collision can even ignite the supermassive black holes at the centers of the galaxies, sending out powerful jets of energy that can be seen across billions of light years. Galactic mergers are more than just a cosmic spectacle, they're a driving force of evolution in the universe. By bringing together vast amounts of gas and triggering star formation, they enrich galaxies with the raw materials needed for new stars, planets, and even life. They also play a crucial role in shaping the large-scale structure of the universe, connecting galaxies into clusters and superclusters that stretch across the cosmos. As we witness these cosmic dances, we're reminded that the universe is anything but static. It's a place of constant change, where even the mightiest galaxies are shaped and reshaped by the forces of gravity and time. But what happens after the collision? What legacy do these galactic mergers leave behind? And how do they influence the next chapter of cosmic evolution? At the heart of nearly every galaxy lies a cosmic enigma, a supermassive black hole. These colossal objects, millions or even billions of times more massive than our Sun, are more than just gravitational traps. They are the unseen engines that shape the destiny of their host galaxies, influencing everything from star formation to the very structure of the cosmos. But how do these mysterious giants form, and what role do they play in the grand story of galactic evolution? Supermassive black holes begin their lives as small seeds, often formed from the remnants of massive stars that collapsed at the end of their lives. Over time, they grow by consuming vast amounts of gas, dust, and even entire stars. As material spirals into the black hole, it heats up, releasing enormous amounts of energy in the form of light and radiation. This process is so intense that it can outshine all the stars in the galaxy combined, creating what astronomers call an active galactic nucleus, or AN. One of the most dramatic examples of an AGN is a quasar. Quasars are among the brightest objects in the universe, shining with the light of trillions of stars. Despite their incredible luminosity, quasars are powered by regions no larger than our solar system, the supermassive black holes at their cores. Imagine a single object, smaller than the distance between the Sun and Pluto, capable of producing more energy than an entire galaxy. It's a testament to the sheer power of these cosmic behemoths, but supermassive black holes don't just consume, they also give back. The energy they release can heat up surrounding gas, preventing it from collapsing to form new stars. In this way, black holes act as cosmic regulators, controlling the growth of their host galaxies. This feedback mechanism is crucial to understanding why some galaxies stop forming stars, becoming red and dead as their gas reservoirs are depleted. The relationship between supermassive black holes and their galaxies is a delicate dance. As the black hole grows, its influence spreads, shaping the galaxy's evolution in profound ways. For instance, the jets of particles and radiation emitted by some black holes can travel millions of light years, carving out vast bubbles in the surrounding gas and even influencing the formation of neighboring galaxies. Take the galaxy M87, for example. At its center lies a supermassive black hole, weighing in at an astonishing 6.5 billion times the mass of our Sun. In 2019, the Event Horizon Telescope captured the first ever image of this black hole's shadow, a groundbreaking achievement that brought the mysteries of these objects into sharp focus. The image revealed the intense gravitational forces at work, bending light and warping space-time itself. Supermassive black holes are more than just cosmic curiosities, they are key players in the story of galactic evolution. By regulating star formation and shaping the structure of galaxies, they ensure that the universe remains a dynamic, ever-changing place, but their influence doesn't stop there. As we continue to explore their role, we uncover new connections between these enigmatic objects and the larger tapestry of the cosmos. So, what happens when galaxies grow old and their stars begin to fade? How do these cosmic giants meet their end, and what legacy do they leave behind? That's where the story takes its final, poignant turn. Spiral galaxies are the crown jewels of the cosmos, grand, swirling structures that captivate our imagination with their beauty and complexity. Take the Milky Way, our cosmic home, as an example. Its graceful arms, studded with stars, gas, and dust, spiral outward from a bright central bulge, creating a mesmerizing pattern that has inspired countless stargazers. But how do these iconic structures form, and what keeps them spinning in such perfect harmony? The secret lies in something called density waves. Picture a ripple moving across the surface of a pond, creating patterns that shift and flow. In a spiral galaxy, density waves act in a similar way, compressing gas and dust as they move through the galactic disk. This compression triggers the birth of new stars, lighting up the spiral arms like a cosmic neon sign. Over time, these waves travel through the galaxy, creating the stunning spiral patterns we see today. Rotation plays a key role in shaping these galaxies. As a spiral galaxy spins, centrifugal force pushes material outward while gravity pulls it back in. This delicate tug of war maintains the galaxy's balance, keeping its arms intact and its structure stable. Without this rotation, the galaxy's spiral arms would collapse, losing their iconic shape. The Whirlpool Galaxy, located about 23 million light-years from Earth, offers a stunning example of this process in action. Its tightly wound arms are alive with star formation, their bright blue clusters contrasting with the darker lanes of dust. These arms aren't static, they're dynamic, ever-changing regions where stars are born, live, and die, shaping the galaxy's evolution over billions of years. But spiral galaxies aren't the only players in the cosmic story. In contrast, elliptical galaxies present a completely different picture. These smooth, football-shaped collections of stars lack the intricate arms of their spiral counterparts. Instead, they're dominated by older, redder stars, with little gas or dust to fuel new star formation. The difference lies in their history. Elliptical galaxies often form through the collision and merger of spiral galaxies, a process that disrupts their delicate structure and halts the formation of new stars. This contrast between spiral and elliptical galaxies highlights the incredible diversity of the universe. While spirals are vibrant and dynamic, constantly evolving through star formation and rotation, ellipticals are quiet and ancient, their stories written in the fading glow of old stars. Together, they remind us that the cosmos is a place of endless variety, where even the simplest structures hold profound secrets. As we marvel at the beauty of spiral galaxies, we're reminded of the intricate processes that shape the universe. From the density waves that carve their arms to the rotation that keeps them spinning, these galaxies are a testament to the delicate balance that governs the cosmos. And as we turn our gaze to the broader universe, we begin to see how these processes connect, weaving a tapestry of creation and transformation that stretches across the ages. Elliptical galaxies are the silent giants of the universe, vast, smooth, and often featureless. They stand in stark contrast to the vibrant spirals we're so familiar with. Unlike the swirling arms of the Milky Way or the Whirlpool Galaxy, ellipticals are shaped more like footballs or spheres, their stars distributed evenly in every direction. But how do these cosmic behemoths come to be? The answer lies in one of the most dramatic events in the cosmos, galactic collisions. When two spiral galaxies collide, the result is nothing short of transformative. Picture two dancers, each with their own rhythm and grace, suddenly thrown into a chaotic embrace. As their stars and gas clouds intertwine, the delicate spiral structures are torn apart. The gas, once the fuel for star formation, is either flung out into intergalactic space or funneled toward the supermassive black holes at the galaxy's centers. Without this gas, new stars can no longer form, and the galaxy begins to age. Over time, the chaotic orbits of stars settle into a more uniform, elliptical shape, creating the smooth, featureless appearance we see today. Take the galaxy M87, for example. Located at the heart of the Virgo cluster, it's one of the largest and most massive galaxies known. Its smooth, golden glow is a testament to its age, with few signs of the star-forming regions that light up younger galaxies. Instead, M87 is dominated by older, redder stars, their light a faint echo of the galaxy's more dynamic past. But M87 isn't just a relic, it's a powerhouse, its supermassive black hole emitting jets of energy that stretch thousands of light years into space. Elliptical galaxies like M87 often dominate galaxy clusters, their immense gravity shaping the structure of their surroundings. They're the cosmic elders, their stories written in the fading glow of stars that have burned for billions of years. And while they may lack the intricate beauty of spirals, their simplicity is a reminder of the universe's capacity for change. This transformation from spiral to elliptical is a key part of galactic evolution, but it's not the only path. Some galaxies remain spirals for billions of years, while others evolve into irregular shapes or even merge into entirely new forms. The diversity of galaxies is a reflection of the universe's complexity, each type telling a unique story of creation, destruction, and renewal. As we explore these different galactic forms, we begin to see how the universe is a dynamic, ever-changing tapestry. From the birth of stars in spiral arms to the quiet aging of ellipticals, every galaxy has a role to play in the grand narrative of cosmic evolution. But what happens when galaxies reach the end of their journey? What becomes of these ancient giants, and how do their stories shape the universe around them? Gas is the lifeblood of galaxies, a raw, elemental ingredient that fuels the birth of stars, shapes the structure of galaxies, and even powers the supermassive black holes at their cores. Without gas, galaxies would be little more than static collections of aging stars, their brilliance fading into the cosmic void. But how do galaxies acquire this vital resource, and what happens when they lose it? The story of gas in galactic evolution is a tale of cosmic cycles, where galaxies breathe in and out, their destinies shaped by the ebb and flow of this essential material. Galaxies acquire gas in several ways. One of the most significant is through accretion, the process by which galaxies pull in gas from their surroundings. Picture a galaxy as a cosmic sponge, soaking up the hydrogen and helium that permeates the universe. This gas often flows along the filaments of the cosmic web, the vast network of dark matter that connects galaxies across the cosmos. As the gas falls into a galaxy's gravitational well, it cools and condenses, forming the dense clouds that give birth to new stars. But galaxies don't just collect gas, they also lose it. Galactic winds, driven by supernova explosions and the intense radiation from young stars, can blow gas out of a galaxy, scattering it into intergalactic space. These winds are like cosmic gusts, carrying away the very material that fuels star formation. In some cases, the winds are so powerful that they strip a galaxy of its gas entirely, leaving it unable to form new stars. This process is particularly common in starburst galaxies, where rapid star formation generates intense winds that can reshape the galaxy's future. Take the Magellanic Clouds, for example. These two small galaxies, orbiting the Milky Way, are rich in gas, making them ideal laboratories for studying star formation. The Large Magellanic Cloud, in particular, is home to the Tarantula Nebula, one of the most active star-forming regions in the local universe. Here, vast clouds of gas collapse under their own gravity, igniting the fires of new stars. But even these gas-rich galaxies aren't immune to the effects of galactic winds. As stars are born and die, they send shockwaves through the gas, creating a dynamic and ever-changing environment. Gas doesn't just fuel star formation, it also feeds the supermassive black holes at the centers of galaxies. As gas spirals toward these black holes, it heats up, releasing enormous amounts of energy in the form of light and radiation. This process, known as accretion, can turn a quiet black hole into an active galactic nucleus, outshining all the stars in the galaxy combined. In some cases, the energy released by the black hole can even halt star formation, heating the surrounding gas and preventing it from collapsing into new stars. The availability of gas plays a crucial role in shaping a galaxy's destiny. Gas-rich galaxies, like the Magellanic Clouds, are vibrant and dynamic, teeming with young stars and active star-forming regions. In contrast, gas-poor galaxies, often found in the centers of galaxy clusters, are quiet and aging, their stars growing older with little hope of renewal. This difference highlights the delicate balance that governs galactic evolution, a balance between the inflow and outflow of gas, between creation and destruction. As we explore the role of gas in galactic evolution, we begin to see how this simple element shapes the universe on the grandest scales. From the birth of stars to the feeding of black holes, gas is the thread that weaves together the story of cosmic evolution. And as we look to the future, we're reminded that the universe is a place of constant change, where even the smallest fluctuations can have profound and lasting effects. But what happens when a galaxy's gas is depleted and its stars begin to fade? What becomes of these aging giants, and how do they influence the universe around them? That's where the story takes its next, inevitable turn. Galactic winds are like the breath of a galaxy, powerful, invisible forces that shape its destiny in ways we're only beginning to understand. These winds, driven by the explosive energy of supernova and the intense radiation from supermassive black holes, are more than just cosmic gusts. They're transformative, capable of ejecting gas from galaxies and altering their evolution on a grand scale. But what exactly are galactic winds, and how do they influence the cosmic ecosystem? At their core, galactic winds are vast streams of gas and particles that flow out of galaxies at incredible speeds, sometimes reaching hundreds of kilometers per second. These outflows are triggered by the intense energy released during supernova explosions, or by the radiation and jets emitted from active galactic nuclei. Imagine a galaxy as a living, breathing entity. When it exhales, it sends ripples of gas and dust into the surrounding void, creating a dynamic interplay between creation and destruction. One of the most dramatic effects of galactic winds is their ability to regulate star formation. As stars are born and die in rapid succession, they release enormous amounts of energy, driving gas out of the galaxy. This loss of gas can slow or even halt the formation of new stars, effectively putting a galaxy's growth on pause. In this way, galactic winds act as cosmic regulators, ensuring that galaxies don't burn through their fuel too quickly. Starburst galaxies provide a striking example of this process in action. These galaxies, like Messier 82, are hotspots of star formation, producing new stars at a rate hundreds of times faster than the Milky Way. But this rapid pace comes at a cost. The intense supernova explosions and radiation from young stars generate powerful galactic winds, which blow gas out of the galaxy at incredible speeds. Over time, this loss of gas can leave the galaxy unable to form new stars, transforming it from a vibrant nursery into a quiet, aging system. But galactic winds don't just affect the galaxies they originate from. They also play a crucial role in enriching the intergalactic medium, the vast expanse of gas that fills the space between galaxies. As these winds carry gas and heavy elements out of their host galaxies, they spread these materials across the cosmos. These elements, forged in the hearts of stars and supernova, become the building blocks for future generations of stars, planets, and even life. This process creates a cosmic feedback loop, where the evolution of galaxies is intricately connected to the larger structure of the universe. Galactic winds help shape the cosmic web, the vast network of dark matter and gas that connects galaxies across the cosmos. By redistributing gas and heavy elements, they ensure that the universe remains a dynamic, ever-changing place. As we explore the impact of galactic winds, we begin to see how these invisible forces shape the story of cosmic evolution. From regulating star formation to enriching the intergalactic medium, they play a vital role in the life cycle of galaxies. And as we turn our gaze to the broader universe, we're reminded that even the smallest processes can have profound and lasting effects, weaving together the tapestry of creation that stretches across the ages. But what happens when a galaxy's winds blow too fiercely, stripping it of its gas and leaving it unable to form new stars? How do these aging systems continue to influence the cosmos, and what legacy do they leave behind? That's where the story takes its next, fascinating turn. The universe isn't just a collection of isolated galaxies scattered randomly across the void. It's an intricate, interconnected tapestry, woven together by an invisible framework known as the cosmic web. Picture a spider's web, stretching across unimaginable distances, with galaxies clustered at the intersections of its threads and vast, empty voids in between. This web is the backbone of the universe, a sprawling network of filaments and nodes that guides the flow of gas, dark matter, and even the destiny of galaxies themselves. At the heart of this structure lies dark matter, the unseen architect of the cosmos. While we can't see it directly, its gravitational pull shapes the cosmic web, creating the filaments that connect galaxies across billions of light years. These filaments act like cosmic highways, channeling gas and matter into the gravitational wells where galaxies form and grow. Without this intricate network, the universe would be a very different place, disconnected, chaotic, and devoid of the grand structures we see today. The cosmic web isn't just a static blueprint, it's a dynamic, ever-changing system. Gas flows along these filaments, drawn by gravity into the denser regions where galaxies reside. This process, known as accretion, is how galaxies continue to grow, pulling in fresh material to fuel star formation and feed their supermassive black holes. It's a cosmic cycle, one that ensures galaxies remain vibrant and evolving, even as the universe itself expands. Visualizing the cosmic web is no easy task, but astronomers have developed stunning simulations to bring this invisible structure to life. These models reveal a universe teeming with activity, where filaments of dark matter and gas stretch across the cosmos like rivers of light. At their intersections, galaxies cluster together, forming the nodes of the web. These clusters, some containing thousands of galaxies, are the largest structures in the universe, bound together by gravity and the flow of material along the filaments. But the cosmic web isn't just about structure, it's also about emptiness. Between the filaments lie vast voids, regions of space that are almost entirely empty of matter. These voids are like cosmic deserts, stretching for hundreds of millions of light years. Yet, even here, the influence of the web is felt. The boundaries between filaments and voids are where galaxies often form, their growth driven by the flow of material from the emptier regions into the denser ones. This interplay between filaments, nodes, and voids shapes the evolution of galaxies in profound ways. For instance, galaxies in dense clusters tend to evolve differently than those in more isolated regions. In clusters, galaxies are more likely to collide and merge, triggering bursts of star formation and feeding their central black holes. In contrast, galaxies in the quieter, less dense regions of the web may evolve more slowly, their growth dictated by the steady trickle of gas along the filaments. The cosmic web is more than just a map of the universe. It's a living, breathing system that connects galaxies across time and space. By understanding its structure and dynamics, we gain insight into how galaxies form, grow, and evolve, and how the universe itself has come to take the shape we see today. As we explore this vast network, we begin to see how every galaxy, every star, and every planet is part of a larger story, one that stretches back to the dawn of time and forward into the distant future. And as we trace the threads of the cosmic web, we're reminded of the profound interconnectedness of the cosmos, a universe where even the smallest structures are part of a grand, ever-unfolding design. So, what happens when we zoom out even further, beyond the cosmic web, to explore the universe on its largest scales? How does the structure of the web influence the fate of galaxies? And what secrets does it hold about the origins of the cosmos itself? That's where our journey takes its next, awe-inspiring turn. Galaxy clusters are the bustling metropolises of the cosmos, colossal gatherings of hundreds, even thousands, of galaxies bound together by the relentless pull of gravity. These clusters are the largest structures in the universe, sprawling across millions of light years and containing enough mass to warp the very fabric of space-time. Within their borders, galaxies swirl and collide in a cosmic dance, their interactions shaping the evolution of the cluster itself and the broader universe beyond. At the heart of every galaxy cluster lies a supermassive black hole, often surrounded by a halo of hot gas that glows brightly in X-rays. This gas, heated to millions of degrees, fills the space between galaxies, creating a dynamic and energetic environment. But it's not just gas that holds these clusters together. Dark matter plays a crucial role, acting as the invisible glue that binds galaxies into these massive structures. Without dark matter, galaxy clusters would simply fly apart, their galaxies scattering into the void. One of the most famous examples is the Virgo cluster, located about 54 million light-years from Earth. Home to over 2,000 galaxies, including the giant elliptical galaxy M87, the Virgo cluster is a cosmic powerhouse. Its galaxies are constantly interacting, their gravitational forces pulling them into close encounters that can trigger bursts of star formation or even merge them into larger galaxies. These collisions are not just chaotic, they're transformative, reshaping the galaxies and the cluster itself over billions of years. But galaxy clusters are more than just collections of galaxies, they're also immense reservoirs of hot gas. This gas, while invisible to the naked eye, emits X-rays that reveal its presence. It's a key player in the cluster's evolution, influencing everything from star formation to the growth of supermassive black holes. As galaxies move through the cluster, they can strip gas from one another, creating long, luminous tails that stretch across the void. This process, known as ram pressure stripping, can leave galaxies gas poor, halting their star formation and altering their destiny. The role of galaxy clusters extends far beyond their borders. These cosmic metropolises are connected by the filaments of the cosmic web, the vast network of dark matter and gas that spans the universe. Clusters often form at the intersections of these filaments, where gravity pulls in material from the surrounding regions. In this way, clusters act as cosmic hubs, drawing in gas, galaxies, and even other clusters, shaping the large-scale structure of the universe. As we explore these immense structures, we begin to see how they influence the broader story of cosmic evolution. Galaxy clusters are not just endpoints, they're part of an ongoing process where galaxies collide, merge, and evolve, creating new structures and driving the growth of the universe itself. They remind us that the cosmos is a place of constant change, where even the largest structures are shaped by the subtle interplay of gravity, gas, and dark matter. Looking ahead, we see how these clusters fit into the grand tapestry of the universe, their role extending far beyond their own boundaries. But what happens when we zoom out even further to explore the universe on its largest scales? How do these clusters and the cosmic web that connects them influence the fate of the cosmos itself? That's where our journey takes its next, breathtaking turn. While giant galaxies like the Milky Way and Andromeda often steal the spotlight, the universe is teeming with smaller, more humble structures, dwarf galaxies. These cosmic underdogs, though small in size, play a colossal role in the grand story of galactic evolution. Dwarf galaxies are the most numerous galaxies in the universe, often orbiting larger galaxies like satellites, their fates intricately tied to the giants they accompany. But don't let their size fool you. These tiny galaxies are powerhouses of cosmic activity, shaping the universe in ways that are only beginning to be understood. Dwarf galaxies typically contain just a few billion stars, a tiny fraction compared to the hundreds of billions in larger galaxies like our own. They often lack the intricate spiral arms or smooth elliptical shapes of their larger counterparts, appearing instead as irregular, patchy collections of stars and gas. Yet, despite their modest appearance, dwarf galaxies are incredibly diverse. Some are bursting with star formation, their gas clouds glowing with the light of newborn stars, while others are ancient and quiet, their stars having burned out long ago. One of the most famous examples is the Large Magellanic Cloud, a dwarf galaxy located just 160,000 light-years from Earth. This galaxy, visible from the southern hemisphere as a faint, cloudy patch, is a hub of activity. Its gas-rich regions, like the Tarantula Nebula, are among the most active star-forming areas in the local universe. Here, stars are born in rapid succession, their light illuminating the surrounding gas and dust. The Large Magellanic Cloud isn't just a cosmic neighbor, it's a living laboratory, offering a glimpse into the processes that drive galactic evolution on a smaller scale. But dwarf galaxies aren't just fascinating in their own right, they're also key players in the evolution of larger galaxies. Many dwarf galaxies orbit larger ones, their gravitational interactions leading to mergers over billions of years. When a dwarf galaxy merges with a larger one, it donates its gas, stars, and even dark matter, contributing to the growth of its host. This process, known as hierarchical merging, is one of the primary ways larger galaxies grow and evolve. Take the Milky Way, for example. Our galaxy is surrounded by dozens of dwarf galaxies, some of which are being slowly pulled apart by its gravity. Over time, these dwarfs will merge with the Milky Way, their stars and gas becoming part of our galaxy's structure. This process isn't just a one-time event, it's a continuous cycle, with dwarf galaxies acting as building blocks for the larger structures we see today. Dwarf galaxies also play a crucial role in enriching the cosmic ecosystem. Their gas clouds, often rich in heavy elements forged in supernova, seed the universe with the raw materials needed for future generations of stars and planets. When dwarf galaxies merge with larger ones, they bring these elements with them, ensuring that the cycle of creation continues. Yet, the story of dwarf galaxies is also one of fragility. Their small size makes them vulnerable to the gravitational forces of larger galaxies, often leading to their eventual destruction. Some dwarf galaxies are stretched into long, glowing streams of stars by the tidal forces of their hosts, their remains scattered across the galaxy's outskirts. These tidal streams, like cosmic fingerprints, are a testament to the ongoing interactions that shape the universe. As we explore the role of dwarf galaxies, we begin to see how these small, often overlooked structures are integral to the cosmic narrative. From fueling star formation to building up larger galaxies, they are the unsung heroes of galactic evolution. And as we turn our gaze to the broader universe, we're reminded that even the smallest players can have an outsized impact, weaving their stories into the grand tapestry of the cosmos. But what happens when we zoom out even further, beyond individual galaxies and clusters, to explore the universe on its largest scales? How do these interactions, from the tiniest dwarf galaxies to the mightiest clusters, shape the fate of the cosmos itself? That's where our journey takes its next, awe-inspiring turn. At the heart of every galaxy's story lies a delicate dance, a balance between creation and regulation, where the forces of feedback play a starring role. Feedback is the cosmic thermostat, a process that ensures galaxies don't grow too fast or burn out too soon. Without it, galaxies would either collapse under their own weight or explode in a frenzy of unchecked star formation. But what exactly is feedback, and how does it shape the evolution of galaxies over billions of years? Feedback begins with the life and death of stars. When massive stars reach the end of their lives, they explode as supernova, releasing staggering amounts of energy into their surroundings. This energy heats up the surrounding gas, preventing it from collapsing to form new stars. It's like a cosmic reset button, ensuring that star formation happens in controlled bursts rather than a runaway explosion. Without this regulation, galaxies would exhaust their gas reserves far too quickly, leaving them unable to form new stars or sustain their growth. But supernovae aren't the only players in this process. At the centers of most galaxies, supermassive black holes also contribute to feedback, often in even more dramatic ways. When gas spirals into these black holes, it heats up and releases torrents of energy in the form of radiation and powerful jets. These jets can blast gas out of the galaxy entirely, halting star formation and reshaping the galaxy's structure. This process, known as active galactic nucleus feedback, is one of the most powerful forces in the universe, capable of influencing not just individual galaxies but entire clusters. Take the Milky Way as an example. While our galaxy's central black hole, Sagittarius A, is relatively quiet today, it hasn't always been so serene. In the past, it may have gone through periods of intense activity, its jets and radiation shaping the flow of gas throughout the galaxy. Even now, supernovae in the Milky Way's spiral arms continue to regulate star formation, ensuring that our galaxy remains a vibrant, evolving system rather than a static collection of aging stars. Feedback isn't just about stopping star formation, it's also about creating the conditions for future growth. By heating and redistributing gas, feedback ensures that galaxies have a steady supply of material to draw from over billions of years. This balance between feedback and accretion, the process of pulling in new gas from the cosmic web, is what keeps galaxies alive and evolving. It's a cosmic seesaw, where too much feedback can stifle growth, while too little can lead to chaos. Over time, feedback shapes galaxies in profound ways. In younger galaxies, where star formation is rampant, feedback helps regulate the pace of growth, ensuring that they don't burn through their gas too quickly. In older galaxies, feedback can shut down star formation entirely, leaving them as quiet, aging systems dominated by older stars. This process is a key part of why galaxies evolve so differently over time, from the vibrant spirals of their youth to the smooth ellipticals of their later years. As we explore the role of feedback in galactic evolution, we begin to see how this delicate balance shapes the universe on the grandest scales. It's a process that connects the smallest stars to the largest galaxies, weaving together the story of cosmic evolution in a way that's both awe-inspiring and deeply interconnected. But what happens when feedback fails, or when galaxies lose their ability to regulate their growth? How do these imbalances shape the fate of galaxies, and what do they tell us about the universe's past and future? That's where the story takes its next, fascinating turn. Galaxies don't exist in isolation, they're shaped by the environments they inhabit, from the quiet solitude of cosmic voids to the bustling chaos of galaxy clusters. Just as a tree's growth depends on the soil and climate around it, a galaxy's evolution is deeply influenced by its surroundings. Whether it's nestled in a dense cluster or drifting alone in the vast expanse of space, a galaxy's environment can determine its fate, dictating how it grows, evolves, and even how it dies. Take the Coma cluster, for example. Located about 330 million light-years from Earth, this massive cluster is home to thousands of galaxies, each jostling for space in a crowded cosmic neighborhood. Here, galaxies don't evolve in peace. They are constantly interacting, colliding, and being shaped by the intense gravitational forces around them. One of the most dramatic processes at work is ram pressure stripping, a phenomenon where the hot gas filling the cluster's environment acts like a cosmic wind, stripping gas from individual galaxies as they move through it. Imagine a galaxy as a ship sailing through a storm. As it travels through the cluster, the pressure from the surrounding gas can tear away its own gas clouds, leaving it starved of the material needed to form new stars. This process is particularly devastating for spiral galaxies, whose delicate arms of gas and dust are vulnerable to being stripped away. Over time, these galaxies can lose their ability to form stars, transforming from vibrant, star-forming spirals into quiet, aging ellipticals. But ram pressure stripping isn't the only way a galaxy's environment shapes its evolution. In dense clusters, galaxies are also more likely to collide and merge, their gravitational interactions triggering bursts of star formation or feeding the supermassive black holes at their centers. These collisions can completely reshape a galaxy, altering its structure and even its identity. A spiral galaxy, for instance, might lose its arms in a collision, becoming a smooth, featureless elliptical. On the other end of the spectrum are galaxies in isolation, drifting in the quiet regions of the cosmic web. These galaxies, often found in the voids between clusters, evolve in a very different way. Without the intense gravitational forces or hot gas of a cluster, they grow more slowly, their star formation driven by the steady trickle of gas along the filaments of the cosmic web. These galaxies are like cosmic hermits, their evolution dictated by their own internal processes rather than the chaos of a crowded environment. The contrast between galaxies in clusters and those in isolation highlights the profound influence of environment on galactic evolution. In clusters, galaxies are shaped by external forces, ram pressure stripping, collisions, and the intense gravitational pull of their neighbors. In isolation, they're free to grow at their own pace, their evolution driven by the slow accretion of gas and the internal feedback from stars and black holes. But even in the most extreme environments, galaxies find ways to adapt. Some develop thick layers of gas and dust to shield themselves from the stripping effects of ram pressure. Others form dense, compact cores that are more resistant to disruption. These adaptations are a testament to the resilience of galaxies, their ability to survive and thrive in even the harshest conditions. As we explore the impact of environment on galactic evolution, we begin to see how the universe is a dynamic, interconnected system, where every galaxy is shaped by the world around it. From the bustling clusters to the quiet voids, the environment leaves its mark on every galaxy, weaving a story of creation, destruction, and adaptation that spans billions of years. So, what happens when we zoom out even further to explore the universe on its largest scales? How do these environmental forces shape the fate of galaxies across the cosmos? And what can they tell us about the universe's past and future? That's where our journey takes its next, awe-inspiring turn. Time is the silent architect of the cosmos, shaping galaxies over spans so vast they defy human imagination. To understand galactic evolution, we must think not in centuries or millennia, but in billions of years, a timescale where even the slowest processes leave profound marks. Every galaxy we see today is the product of an intricate dance with time, a story written in the aging of stars, the expansion of the universe, and the relentless pull of gravity. But how do these forces work together to shape galaxies, and what can we learn by peering into the distant past? One of the most remarkable tools astronomers use to study galactic evolution is the Hubble Deep Field, a tiny patch of sky that, when observed in detail, reveals thousands of galaxies at various stages of their lives. This image is like a cosmic time machine, capturing galaxies as they appeared billions of years ago. By studying these distant galaxies, astronomers can piece together the story of how galaxies have grown and changed over time. What they've found is a universe in constant motion, where galaxies evolve from small, chaotic systems into the majestic structures we see today. But time doesn't just reveal the past, it also shapes the future. As the universe expands, galaxies are carried along on this cosmic tide, their distances from one another growing ever larger. This expansion isn't just about space stretching, it's a fundamental force that influences how galaxies evolve. For example, as the universe ages, the gas available for star formation becomes more diffuse, making it harder for galaxies to form new stars. Over time, this leads to a gradual decline in star formation, a process astronomers call cosmic downsizing. The aging of stars also plays a crucial role in galactic evolution. Massive stars, though dazzling in their youth, burn through their fuel quickly, ending their lives in supernova explosions that enrich the galaxy with heavy elements. These elements become the building blocks for new stars and planets, ensuring that the galaxy continues to evolve. Meanwhile, smaller stars, like our Sun, burn steadily for billions of years, their light gradually fading as they age. Over time, these processes shape the galaxy's population of stars, transforming it from a vibrant, star-forming system into a quieter, more mature one. As we look to the future, we see that galaxies are not static, they continue to change, shaped by the relentless passage of time. The Milky Way, for instance, is on a collision course with the Andromeda galaxy, a merger that will reshape both galaxies over the next 4 billion years. Such events are a reminder that galactic evolution is an ongoing process, one that will continue to unfold long after our own star has faded. By studying the role of time in galactic evolution, we gain a deeper understanding of the universe's history and its ultimate fate. From the birth of the first stars to the distant future of galaxy mergers, time is the thread that weaves together the story of cosmic evolution. And as we explore this vast tapestry, we're reminded that the universe is a place of constant change, where even the slowest processes leave an indelible mark. But what happens when we zoom out even further, beyond individual galaxies and their timelines, to explore the universe on its largest scales? How do the forces that shape galaxies also shape the cosmos as a whole? That's where our journey takes its next, awe-inspiring turn. The Milky Way, our cosmic home, has been a stable haven for billions of years, its spiral arms gracefully swirling through the void. But this stability won't last forever. Like all galaxies, the Milky Way is on a collision course with its destiny, a fate that will reshape everything we know. In roughly 4 billion years, our galaxy will collide with its nearest neighbor, the Andromeda galaxy, in one of the most dramatic events in cosmic history. This collision won't just be a fleeting moment, it will unfold over hundreds of millions of years, a slow-motion dance that will transform both galaxies into something entirely new. Using advanced simulations, astronomers have been able to visualize this cosmic merger in stunning detail. At first, the two galaxies will approach each other, their gravitational forces pulling them closer. As they near, their spiral arms will begin to distort, stretching into long, luminous streams of stars and gas. The galaxies will pass through one another, their stars and gas clouds intermingling in a chaotic yet beautiful display. But this isn't the end. Gravity will pull them back together, and over time, they will merge into a single, massive elliptical galaxy. Astronomers have even given this future galaxy a name, Milky Way. What does this mean for us? For our Sun and Earth, the collision will be a mix of chaos and calm. Stars are so far apart in galaxies that the chances of our solar system colliding with another star are astronomically low. However, the gravitational forces at play could fling the Sun and its planets into a new orbit, sending us hurtling through the outskirts of this new galaxy. Earth, if it still exists by then, might find itself in a very different part of the cosmos, surrounded by a night sky filled with unfamiliar stars. But the collision of the Milky Way and Andromeda isn't just a local event, it's part of a much larger story. Across the universe, galaxies are constantly colliding and merging, their interactions shaping the cosmos on the grandest scales. These mergers are a driving force of galactic evolution, creating new structures and triggering waves of star formation. They also play a crucial role in the growth of supermassive black holes, which often merge during these collisions, releasing enormous amounts of energy. As we look to the future, we see a universe that is anything but static. Galactic collisions like the one between the Milky Way and Andromeda are a reminder that the cosmos is in constant motion, its structures forever evolving. These events don't just shape individual galaxies, they influence the broader universe, connecting galaxies into clusters and superclusters that stretch across billions of light years. The story of the Milky Way's future is a glimpse into the larger narrative of cosmic evolution. It's a story of creation and transformation, where even the mightiest galaxies are shaped by the forces of gravity and time. And as we peer into the distant future, we're reminded that the universe is a place of endless change, where every collision, every merger, and every new galaxy tells a part of the grand cosmic story. But what happens when we zoom out even further, beyond individual galaxies and their collisions, to explore the universe on its largest scales? How do these galactic interactions shape the fate of the cosmos itself? And what can they tell us about the ultimate destiny of the universe? That's where our journey takes its next, awe-inspiring turn. To truly understand the intricate dance of galaxies, scientists have turned to a tool as vast and complex as the cosmos itself: computer simulations. These digital laboratories allow us to recreate the universe on a scale that would otherwise be impossible, modeling the interactions of dark matter, gas, and stars over billions of years. By running these simulations, researchers can test theories, predict outcomes, and uncover the hidden processes that shape galactic evolution. One of the most groundbreaking projects in this field is Illustris-TNG, a state-of-the-art simulation that has revolutionized our understanding of how galaxies form and grow. This simulation doesn't just focus on one galaxy, it models an entire virtual universe, complete with millions of galaxies, each interacting with the others in a cosmic web of gravity and gas. From the birth of the first stars to the collision of massive galaxies, Illustris-TNG captures it all, offering a glimpse into the universe's most dramatic moments. But creating these simulations is no small feat. The sheer complexity of galactic interactions requires immense computational power, with simulations often running on some of the world's most advanced supercomputers for months at a time. Scientists must account for countless variables, from the gravitational pull of dark matter to the explosive energy of supernova. Even then, challenges remain. For instance, simulating the intricate details of star formation, a process that occurs on relatively small scales, while also modeling the vast expanse of a galaxy, is a constant balancing act. Despite these challenges, simulations have led to remarkable breakthroughs. They've helped us understand how galaxies grow by pulling in gas from their surroundings, how mergers shape their structures, and even how supermassive black holes influence their evolution. Simulations have also revealed the role of feedback energy released by stars and black holes in regulating star formation and maintaining the delicate balance that keeps galaxies alive. What makes simulations truly invaluable is their ability to complement observations. While telescopes allow us to see the universe as it is, simulations show us how it could be. They let us explore hypothetical scenarios, like what might happen if two galaxies collide or how a galaxy might evolve in a different environment. By comparing these virtual universes with real observations, scientists can refine their models, uncovering new insights into the forces that shape the cosmos. As we continue to push the boundaries of what simulations can achieve, they're becoming an essential tool in our quest to understand the universe. They bridge the gap between theory and observation, offering a dynamic, ever-evolving picture of galactic evolution. And as we delve deeper into these digital universes, we're reminded that the story of galaxies is not just written in the stars, it's also encoded in the algorithms and equations that bring them to life. With simulations shedding light on the hidden processes of galactic evolution, we're better equipped to explore the universe's greatest mysteries. But how do these digital discoveries translate into real-world observations? And what can they tell us about the future of our cosmic journey? That's where the story takes its next compelling turn. For centuries, telescopes have been humanity's windows to the cosmos, allowing us to peer into the depths of space and unravel the mysteries of galactic evolution. These instruments, from the earliest refracting telescopes to the most advanced observatories in space, have transformed our understanding of how galaxies form, grow, and change over time. But what makes observational astronomy so powerful is its ability to capture light across the entire electromagnetic spectrum, each wavelength revealing a different piece of the galactic puzzle. Take visible light, for example. When we look at galaxies through optical telescopes, we see the familiar glow of stars, the intricate swirls of spiral arms, and the dusty lanes of nebulae. These images are beautiful, but they only tell part of the story. To truly understand galaxies, we need to look beyond what our eyes can see. Infrared light, for instance, allows us to peer through the thick clouds of dust that obscure star-forming regions, revealing the hidden nurseries where stars are born. X-rays, on the other hand, expose the high-energy processes at work, such as the superheated gas swirling around supermassive black holes. Space telescopes have been game-changers in this field. The Hubble Space Telescope, launched in 1990, has provided some of the most iconic images of galaxies ever captured. Its observations have revealed galaxies in every stage of evolution, from the chaotic birth pangs of young galaxies in the early universe to the serene glow of ancient ellipticals. Hubble's deep field images, in particular, have opened our eyes to the sheer scale of the cosmos, showing thousands of galaxies in a single frame, each one a snapshot of the universe at a different point in time. But Hubble is just the beginning. The James Webb Space Telescope, launched in 2021, has taken observational astronomy to new heights. With its ability to observe in the infrared, Webb can peer even further back in time, capturing light from the first galaxies that formed after the Big Bang. Already, it has revealed galaxies that existed just a few 100 million years after the universe's birth, structures that challenge our understanding of how quickly galaxies can form and evolve. These telescopes don't just show us distant galaxies, they also reveal the intricate details of our cosmic neighbors. For instance, Hubble and Webb have captured stunning images of the Andromeda galaxy, allowing us to study its star-forming regions, supermassive black hole, and even the motions of its stars in unprecedented detail. These observations help us piece together the life cycle of galaxies, from their birth in the early universe to their eventual mergers and transformations. Yet, the story of observational astronomy doesn't end with space telescopes. Ground-based observatories, equipped with adaptive optics and other cutting-edge technologies, are pushing the boundaries of what we can see. By correcting for the distortions caused by Earth's atmosphere, these telescopes can capture images of galaxies with incredible clarity. Projects like the Atacama Large Millimeter Array, or ALMA, have revealed the cold, dense clouds of gas that serve as the raw material for star formation, while radio telescopes like the Very Large Array have mapped the magnetic fields that shape galaxies on the largest scales. As we continue to develop new technologies, our understanding of galaxies deepens, from the discovery of distant galaxies that challenge our models of cosmic evolution to the detailed observations of our own galactic neighborhood. Observational astronomy has transformed our view of the universe. It's a reminder that the cosmos is not just a place of beauty, but also a vast laboratory where we can test our theories and uncover the secrets of existence. But what's next? How will emerging technologies, from next-generation telescopes to artificial intelligence, revolutionize our understanding of galaxies even further. That's where the story takes its next, thrilling turn. The study of galaxies isn't just reserved for professional astronomers with access to multi-million-dollar telescopes. In fact, some of the most exciting discoveries in galactic research have come from a surprising source: everyday people. Citizen scientists and amateur astronomers are playing an increasingly vital role in helping us understand the universe, proving that you don't need a PhD to contribute to groundbreaking science. From classifying galaxies to spotting supernova, these volunteers are reshaping how we approach the cosmos. One of the most remarkable examples of this is Galaxy Zoo, a project that invites the public to help classify galaxies from telescope images. Launched in 2007, Galaxy Zoo quickly became a global phenomenon, with hundreds of thousands of volunteers signing up to sift through millions of images. The task is simple yet profound. Participants look at images of galaxies and categorize them based on their shapes, whether they're spirals, ellipticals, or something more unusual. This seemingly small act of classification has led to some extraordinary discoveries, including entirely new types of galaxies that had previously gone unnoticed. For instance, in 2009, a Dutch schoolteacher named Hanny van Arkel was participating in Galaxy Zoo when she stumbled upon a strange, green object that didn't fit any known category. This object, later named Hanny's voorwerp, Dutch for Hanny's object, turned out to be a rare phenomenon, a quasar ionization echo, a glowing cloud of gas illuminated by the light of a quasar. This discovery, made by a citizen scientist, opened up new avenues of research into the interactions between quasars and their surroundings. But Galaxy Zoo is just one example. Citizen science projects have also contributed to the study of galaxy clusters, the search for gravitational lenses, and even the detection of supernova. These efforts are more than just a fun way to engage the public. They're essential to advancing our understanding of galactic evolution. With the sheer volume of data being collected by modern telescopes, professional astronomers simply can't analyze it all on their own. Citizen scientists help bridge this gap, providing the human intuition and curiosity that machines can't replicate. Beyond their scientific contributions, these projects have another profound impact. They bring the wonders of the universe closer to home. By involving the public in the process of discovery, projects like Galaxy Zoo foster a deeper connection to the cosmos. They remind us that astronomy isn't just for experts, it's a shared human endeavor, a way for anyone to explore the mysteries of the universe. And in doing so, they inspire the next generation of scientists, sparking curiosity and wonder in people of all ages. The role of citizen science in galactic research highlights the power of collaboration. By combining the expertise of professional astronomers with the enthusiasm and dedication of the public, we're able to uncover new insights into how galaxies form, evolve, and interact. It's a testament to the idea that science is at its best when it's inclusive, when it invites everyone to be a part of the journey. As we look to the future, the role of citizen scientists will only grow, especially as new telescopes and observational technologies generate even more data. But the impact of public engagement goes beyond just the science. It's about building a community of curiosity, one that celebrates the beauty and complexity of the universe. And as we continue to explore the cosmos, we're reminded that the story of galaxies isn't just written by the stars. It's also written by the people who look up at them, asking questions and seeking answers. This collaborative spirit doesn't just enrich the field of astronomy, it transforms it, making it more accessible, more vibrant, and more connected to the world around us. And as we turn our attention to the next chapter of galactic research, we're reminded that the universe is a place of endless discovery, where every pair of eyes can make a difference. Artificial intelligence is revolutionizing the way we study galaxies, transforming the vast and complex field of astronomy into a more precise and efficient science. With the sheer volume of data generated by modern telescopes, millions of images, spectra, and measurements, human analysis alone is no longer enough. Enter AI, a tool that not only accelerates the pace of discovery, but also uncovers patterns and connections that might otherwise go unnoticed. From classifying galaxies to simulating cosmic processes, artificial intelligence is becoming an indispensable ally in our quest to understand the universe. One of the most remarkable applications of AI in galactic studies is its ability to classify galaxies with incredible speed and accuracy. Traditionally, astronomers would manually sort through images, categorizing galaxies based on their shapes, colors, and structures. But with machine learning algorithms, this process has been streamlined. Projects like the Galaxy Zoo initiative, which once relied on citizen scientists, are now being augmented by AI systems that can analyze thousands of images in seconds. These algorithms are trained on vast datasets, learning to recognize subtle features that differentiate spirals from ellipticals or identify rare, irregular galaxies. The result, a faster, more comprehensive understanding of galactic diversity, but AI's role goes far beyond classification. It's also a powerful tool for detecting patterns in astronomical data. For instance, machine learning can sift through massive datasets to identify gravitational lenses' rare phenomena, where the gravity of a massive object bends the light from a more distant galaxy. These lenses are like cosmic magnifying glasses, allowing us to study galaxies that would otherwise be too faint or distant to observe. By automating the search for these events, AI is helping astronomers uncover new insights into the distribution of dark matter and the large-scale structure of the universe. AI is also transforming how we simulate cosmic processes. Creating accurate models of galactic evolution requires simulating the interactions of billions of particles, from dark matter to gas clouds. These simulations, which once took months or even years to run, can now be accelerated using AI-driven techniques. For example, researchers are using neural networks to predict the outcomes of complex simulations, reducing computational time while maintaining accuracy. This allows scientists to explore a wider range of scenarios, from the formation of the first galaxies to the collisions that reshape them. Perhaps one of the most exciting aspects of AI is its potential to uncover entirely new phenomena. By analyzing data in ways that humans might not think to, AI systems can spot anomalies or unexpected patterns that lead to groundbreaking discoveries. In one case, an AI algorithm identified a group of galaxies with unusual properties, sparking further investigation into their origins and evolution. These kinds of discoveries remind us that the universe is full of surprises, and AI is helping us uncover them faster than ever before. As we look to the future, the role of AI in astronomy is only set to grow. From enhancing the capabilities of next-generation telescopes to enabling real-time analysis of astronomical events, artificial intelligence is reshaping how we explore the cosmos. It's a partnership between human curiosity and machine precision, one that promises to deepen our understanding of galactic evolution and unlock new frontiers in space science. With AI pushing the boundaries of what's possible, we're entering an era where the mysteries of the universe are closer than ever to being unraveled. But how will these technological advancements shape the next generation of astronomical research? And what new discoveries might they lead us to? That's where the story takes its next thrilling turn. As we delve deeper into the cosmos, astronomers are no longer relying on just one tool to uncover its secrets. Instead, they're combining multiple sources of information, light, gravitational waves, and even ghostly particles called neutrinos, to paint a fuller picture of the universe. This approach, known as multi-messenger astronomy, is like assembling a cosmic jigsaw puzzle, where each piece reveals a different aspect of the story. By observing the same event through multiple messengers, we gain insights that would be impossible with just one method alone. Take gravitational waves, for example. These ripples in space-time, first detected in 2015, are created by cataclysmic events like the collision of black holes or neutron stars. When two neutron stars collided in 2017, the resulting gravitational waves were detected by observatories like LIGO and Virgo. But the story didn't end there. Within seconds, telescopes around the world picked up a burst of light, a gamma-ray flash, followed by a glow in visible, infrared, and X-ray light. This combination of gravitational waves and light provided a groundbreaking view of the event, revealing not just the collision itself, but also the creation of heavy elements like gold and platinum, which were flung into space. Neutrinos, meanwhile, add another layer to the story. These nearly massless particles, which travel through space at nearly the speed of light, can escape from the most extreme environments, like the cores of supernova or the hearts of active galaxies. While they are incredibly difficult to detect, observatories like IceCube in Antarctica have managed to catch a few. When a neutrino is traced back to its source, such as a distant galaxy with a supermassive black hole, it gives us a direct glimpse into the high-energy processes happening there. Combined with observations in light and gravitational waves, neutrinos help us piece together the full picture of these cosmic powerhouses. Multi-messenger astronomy isn't just about observing individual events, it's about understanding their broader impact. For instance, neutron star mergers don't just produce gravitational waves and bursts of light, they also enrich their host galaxies with heavy elements. These elements, forged in the extreme heat and pressure of the collision, become the building blocks for new stars, planets, and even life. By studying these events across multiple wavelengths, we're learning how galaxies evolve chemically, growing richer in elements over time. The power of multi-messenger astronomy lies in its ability to connect the dots between different cosmic phenomena. It's like turning on multiple lights in a dark room. Suddenly, we can see the entire space, not just fragments. This approach has already transformed our understanding of black holes, neutron stars, and the origins of heavy elements. And as our technology improves, it promises to reveal even more about the universe's most mysterious processes. By combining the strengths of different observational methods, multi-messenger astronomy is revolutionizing how we study galaxies. It's a reminder that the cosmos is a dynamic, interconnected system, where every event tells a part of the larger story. And as we continue to explore, we're not just uncovering the secrets of galaxies, we're rewriting the narrative of the universe itself. This collaborative approach to studying the cosmos is opening doors to discoveries that were once unimaginable. But how will these advancements shape the future of astronomy, and what new mysteries might they help us solve? That's where the story takes its next thrilling turn. Hidden within the fabric of galaxies, an invisible force is at work, shaping their evolution in ways we're only beginning to understand. These are cosmic rays, high-energy particles that zip through the cosmos at nearly the speed of light, carrying with them the echoes of some of the universe's most violent events. While they may sound like something out of science fiction, cosmic rays play a surprisingly tangible role in the life of galaxies, influencing everything from star formation to the structure of the interstellar medium. Cosmic rays are born in the aftermath of cataclysmic explosions, like supernova, or in the intense gravitational environments around supermassive black holes. When a massive star explodes, it doesn't just light up the galaxy, it also sends shockwaves racing through space, accelerating particles to incredible speeds. These particles, now cosmic rays, carry immense energy, capable of traveling vast distances and interacting with the gas and dust that fill the space between stars. One of the most profound ways cosmic rays influence galaxies is by heating the interstellar medium. The vast, diffuse clouds of gas and dust that drift between stars. This heating can prevent gas from cooling and collapsing to form new stars, effectively putting the brakes on star formation. In a sense, cosmic rays act as a cosmic thermostat, regulating the pace at which galaxies grow and evolve. Without them, galaxies might burn through their gas reserves too quickly, leaving them unable to sustain their growth over billions of years. But cosmic rays don't just heat the interstellar medium, they also stir it up. As these high-energy particles travel through a galaxy, they create turbulence in the gas, shaping its structure and influencing how it moves. This turbulence can compress gas clouds, triggering the birth of new stars, or it can disperse them, slowing down star formation. It's a delicate balancing act, one that highlights the intricate interplay between cosmic rays and the material that makes up galaxies. A striking example of cosmic rays in action can be found right here in the Milky Way. Above and below the plane of our galaxy, enormous structures known as the Fermi bubbles stretch for tens of thousands of light years. These bubbles, first discovered by the Fermi Gamma Ray Space Telescope, are filled with high-energy particles, likely accelerated by the supermassive black hole at the center of our galaxy. The Fermi bubbles are a testament to the power of cosmic rays, showing how they can shape the structure of a galaxy on the grandest scales. But cosmic rays aren't just shaped by black holes, they also play a role in feeding them. As these high-energy particles interact with the gas around a black hole, they can heat it up, preventing it from collapsing into the black hole's event horizon. This process, known as feedback, helps regulate the growth of supermassive black holes, ensuring they don't consume their host galaxies entirely. It's another example of how cosmic rays are woven into the fabric of galactic evolution, influencing the delicate balance between creation and destruction. As we explore the role of cosmic rays, we begin to see how these invisible particles are key players in the story of galaxies. From regulating star formation to shaping the interstellar medium, they leave their mark on every corner of the cosmos. And as we look to the future, we're reminded that the universe is full of hidden forces, each one contributing to the grand narrative of cosmic evolution. But what happens when cosmic rays escape their host galaxies, traveling across the vast expanse of intergalactic space? How do these high-energy particles influence the broader universe? And what can they tell us about the origins of the cosmos itself? That's where the story takes its next fascinating turn. While we often think of galaxies as shaped by gravity, stars, and dark matter, there's another invisible force at work, one that's equally fascinating yet far less visible. Magnetic fields, though subtle, weave through the fabric of galaxies, influencing everything from the motion of gas to the birth of stars. These fields are like cosmic threads, quietly shaping the structure and behavior of galaxies in ways that are only beginning to be understood. Take the Milky Way, for example. Our galaxy is permeated by a vast magnetic field, stretching from its central bulge out to the edges of its spiral arms. This field isn't uniform, it twists and turns, creating intricate patterns that influence how gas and dust move through the galaxy. When clouds of gas collapse to form stars, magnetic fields can either help or hinder the process. On one hand, they can slow down the collapse by exerting pressure on the gas. On the other, they can channel gas into dense filaments, creating the perfect conditions for star formation. It's a delicate balance, one that highlights the dual role magnetic fields play in galactic evolution. But how do we study something as elusive as a magnetic field? Unlike stars or gas, magnetic fields don't emit light, making them incredibly difficult to observe directly. Instead, astronomers rely on indirect methods, such as measuring the polarization of light or the alignment of cosmic dust grains. These techniques allow us to map the magnetic fields of galaxies, revealing their strength and direction. For instance, observations of the Milky Way's magnetic field show that it's strongest along the galactic plane, where the density of gas and dust is highest. Modeling magnetic fields is another challenge altogether. Unlike gravity, which is relatively straightforward to calculate, magnetic fields are governed by complex equations that require immense computational power to solve. Simulations must account for the interplay between magnetic fields, gas, and stars, as well as the effects of turbulence and rotation. Despite these challenges, advances in supercomputing have allowed scientists to create increasingly accurate models, shedding light on how magnetic fields shape galaxies over time. One of the most intriguing aspects of galactic magnetic fields is their ability to influence the structure of galactic disks. In spiral galaxies like the Milky Way, magnetic fields can create large-scale patterns, such as spiral arms or rings, that align with the galaxy's overall shape. These patterns aren't just decorative, they play a crucial role in regulating the flow of gas and the formation of stars. For example, magnetic fields can stabilize gas clouds, preventing them from fragmenting too quickly and allowing stars to form more efficiently. Magnetic fields also contribute to the complexity of galactic evolution by interacting with other forces, such as supernova explosions and galactic winds. When a massive star explodes, it sends shockwaves through the galaxy, compressing magnetic fields and amplifying their strength. These amplified fields, in turn, can channel the energy of the explosion, shaping the structure of the surrounding gas and influencing where new stars will form. It's a dynamic feedback loop where magnetic fields both respond to and shape the events around them. As we uncover more about the role of magnetic fields in galaxies, we're beginning to see how these invisible forces are woven into the very fabric of the cosmos. From guiding the birth of stars to shaping the structure of galactic disks, they're a subtle yet vital part of the story of galactic evolution. And as we look to the future, we're reminded that the universe is full of hidden forces, each one contributing to the grand narrative of creation and transformation. But how do these magnetic fields extend beyond individual galaxies, influencing the broader universe? What role do they play in the cosmic web, and how do they connect galaxies across vast distances? That's where the story takes its next fascinating turn. As we've explored the intricate dance of galaxies, from their birth in the early universe to their dramatic collisions and transformations, There's one force that looms large over everything, a force so mysterious that we can't even see it or fully understand it. This is dark energy, the enigmatic driver behind the accelerated expansion of the universe. Unlike gravity, which pulls galaxies together, dark energy acts as a cosmic repellent, pushing galaxies apart and shaping the large-scale structure of the cosmos in profound ways. The story of dark energy begins with a surprising discovery in the late 1990s. Astronomers studying distant supernova found something unexpected. The universe wasn't just expanding, it was expanding faster and faster over time. This observation, which earned the researchers the Nobel Prize, revealed the presence of an invisible force counteracting gravity's pull. Today, we call this force dark energy, and it makes up roughly 68% of the universe's total energy content. But what exactly is it? The truth is, we're still trying to figure that out. One of the most compelling pieces of evidence for dark energy comes from the cosmic microwave background, or CMB, the faint afterglow of the Big Bang. This ancient light, which fills the universe, carries subtle imprints of the early cosmos. By studying these patterns, scientists have been able to map the distribution of dark energy and its influence on the universe's expansion. The CMB tells us that dark energy has been at work since the universe was young, subtly shaping its evolution over billions of years. So, how does dark energy affect galaxies? On the largest scales, it's a game changer. As dark energy accelerates the expansion of the universe, it stretches the cosmic web, the vast network of filaments and nodes that connect galaxies across the cosmos. Over time, this expansion pulls galaxies farther apart, making it harder for them to interact or merge. In a sense, dark energy is isolating galaxies, creating a universe where the distances between them grow ever larger. But the influence of dark energy doesn't stop there. It also shapes the future of galaxies in ways that are both fascinating and a little unsettling. As the universe continues to expand, galaxies will eventually become so far apart that their light will no longer reach one another. Imagine a future where the night sky grows darker and darker as galaxies beyond our local group fade from view. This is the ultimate fate of a universe dominated by dark energy, a lonely, ever-expanding cosmos where galaxies are islands adrift in an endless sea of darkness. Yet, even as dark energy reshapes the universe on the grandest scales, it leaves galaxies themselves relatively untouched. Within galaxy clusters, gravity's pull is strong enough to counteract dark energy's repulsive force, keeping galaxies bound together. This means that, while dark energy determines the fate of the universe as a whole, individual galaxies can continue to evolve, collide, and merge within their local environments. The discovery of dark energy has fundamentally changed our understanding of the cosmos. It's a reminder that the universe is far more complex and mysterious than we once thought, with forces at work that we're only beginning to comprehend. As we continue to study dark energy, we're not just uncovering the secrets of galactic evolution, we're exploring the very nature of the universe itself. But what does the future hold for galaxies in a universe ruled by dark energy? How will this mysterious force shape the ultimate fate of the cosmos? And what can it tell us about the origins of everything we see? That's where the story takes its next, awe-inspiring turn. Galaxy mergers are not just cosmic spectacles, they are the architects of the universe's largest structures, shaping its evolution on scales that defy imagination. These colossal encounters, where galaxies collide and intertwine, are more than just violent events. They are transformative processes that drive the growth of supermassive black holes, ignite bursts of star formation, and forge entirely new galactic forms. Over billions of years, mergers have built the universe as we know it, from the smallest dwarf galaxies to the most massive galaxy clusters. At the heart of every merger lies a profound interplay of forces. When galaxies collide, their supermassive black holes are drawn together, spiraling toward the center of the newly forming system. As these black holes merge, they release staggering amounts of energy in the form of gravitational waves, ripples that ripple through the fabric of space-time. This energy doesn't just vanish, it heats the surrounding gas, preventing it from collapsing to form stars. In this way, mergers act as cosmic regulators, ensuring that galaxies don't grow too quickly or burn out too soon. But mergers are also engines of creation. The collision of galaxies compresses their gas clouds, triggering intense bursts of star formation. These starbursts can light up the merging galaxies, outshining their combined light and creating some of the brightest objects in the universe. The antennae galaxies, located about 45 million light-years from Earth, offer a stunning example of this process in action. These two spiral galaxies, locked in a cosmic dance, are ablaze with new stars, their long, luminous tails stretching across the void like celestial brushstrokes. Over time, mergers transform galaxies in profound ways. Spiral galaxies, with their delicate arms of gas and dust, often lose their structure in a collision, their stars and gas redistributed into a smooth, featureless shape. This process gives rise to elliptical galaxies, the football-shaped giants that dominate the centers of galaxy clusters. These galaxies, though quieter and less dynamic than their spiral counterparts, are the end result of countless mergers, their stars orbiting in a chaotic yet stable dance. Galaxy clusters, the largest structures in the universe, owe their existence to mergers as well. These sprawling metropolises, containing hundreds or even thousands of galaxies, form at the intersections of the cosmic web, where gravity pulls galaxies together into dense, vibrant communities. Over time, these clusters grow through mergers, their galaxies colliding and merging to form ever larger systems. The Coma cluster, located about 330 million light-years from Earth, is a prime example. This massive cluster is home to thousands of galaxies, many of which have undergone mergers, creating a dynamic and ever-changing environment. Yet, the story of galaxy mergers doesn't end in the distant past, they continue to shape the universe today. The Milky Way, for instance, is on a collision course with the Andromeda galaxy, a merger that will unfold over billions of years. While such events may seem rare, they are a natural part of the universe's evolution, a testament to the dynamic and ever-changing nature of the cosmos. As we explore the role of galaxy mergers, we begin to see how these dramatic events are woven into the very fabric of the universe. From the birth of new stars to the creation of galaxy clusters, mergers are a driving force of cosmic evolution, shaping the universe on scales both grand and intimate. And as we look to the future, we're reminded that the cosmos is a place of constant change, where even the mightiest structures are shaped by the forces of gravity and time. But what happens when we zoom out even further, beyond individual galaxies and clusters, to explore the universe on its largest scales? How do these mergers and the forces that drive them influence the fate of the cosmos itself? That's where the story takes its next, awe-inspiring turn. At the heart of nearly every galaxy lies a supermassive black hole, a cosmic powerhouse that not only devours matter, but also shapes the destiny of its host galaxy. These black holes, with masses millions or even billions of times greater than our Sun, are far from passive. They are dynamic engines of feedback, releasing torrents of energy that can either ignite or stifle star formation. This feedback mechanism is one of the most profound forces in galactic evolution, acting as a cosmic thermostat that regulates the growth and life cycle of galaxies. When a supermassive black hole feeds, it doesn't just consume quietly. Gas spiraling into the black hole heats up to incredible temperatures, releasing vast amounts of energy in the form of radiation and powerful jets. These jets, traveling at nearly the speed of light, can extend far beyond the galaxy itself, carving out immense bubbles in the surrounding gas. This process, known as active galactic nucleus and feedback, is not just a spectacular display, it's a critical regulator of star formation. The energy released by these jets can heat the surrounding gas, preventing it from cooling and collapsing into new stars. In this way, AGN feedback acts as a cosmic brake, ensuring that galaxies don't grow too quickly or burn through their fuel too soon. A striking example of this process can be seen in the quasar 3C273, one of the brightest and most studied objects in the universe. Located about 2.4 billion light-years from Earth, 3C273 is powered by a supermassive black hole that's actively consuming matter. Its jets, visible across vast distances, are ejecting material at incredible speeds, shaping the surrounding environment and regulating star formation in its host galaxy. By studying quasars like 3C273, astronomers have gained invaluable insights into how AGN feedback influences galactic evolution, revealing a delicate balance between creation and regulation. But AGN feedback doesn't just suppress star formation, it can also trigger it. In some cases, the shock waves from jets and outflows compress nearby gas clouds, creating the perfect conditions for new stars to form. This dual role highlights the complexity of feedback mechanisms, where the same forces that inhibit star formation in one region can ignite it in another. It's a reminder that galaxies are dynamic systems, shaped by a constant interplay of forces. Over cosmic time, AGN feedback plays a crucial role in shaping the evolution of galaxies, particularly the most massive ones. In these galaxies, the energy released by supermassive black holes can heat the gas to such high temperatures that it becomes unable to cool and form stars. This process, known as quenching, transforms vibrant, star-forming galaxies into quiet, aging systems dominated by older stars. The result is a galaxy that has effectively retired from active star formation, its evolution shaped by the feedback from its central black hole. The impact of AGN feedback extends far beyond individual galaxies. On the largest scales, it helps shape the distribution of gas in the cosmic web, influencing the formation and growth of galaxy clusters. By regulating the flow of gas and the formation of stars, feedback ensures that the universe remains a dynamic, ever-changing place, where galaxies evolve in response to the forces around them. As we explore the role of supermassive black holes and their feedback mechanisms, we begin to see how these enigmatic objects are woven into the very fabric of galactic evolution. From the dazzling jets of quasars to the quiet quenching of massive galaxies, AGN feedback is a driving force that shapes the cosmos on scales both grand and intimate. And as we continue to study these processes, we're reminded that the universe is a place of constant change, where even the mightiest structures are shaped by the subtle interplay of energy, matter, and time. But how do these feedback mechanisms fit into the broader story of the universe? How do they influence the fate of galaxies across cosmic time? And what can they tell us about the origins of the structures we see today? That's where the story takes its next fascinating turn. As we journey deeper into the story of galaxies, we uncover a fascinating truth. Every galaxy carries its own unique history, written in the lives of its stars. This history, known as a galaxy's star formation history, is like a cosmic memoir, a record of when and how stars were born, lived, and died over billions of years. By studying these histories, astronomers can piece together the life story of a galaxy, revealing how it grew, evolved, and became the structure we see today. So, how do astronomers decode these histories? The key lies in the stars themselves. Stars of different ages and compositions tell different stories. Young, massive stars, for instance, burn brightly and die quickly, leaving behind telltale signs of recent star formation. Older stars, on the other hand, glow with a quieter, steadier light, hinting at quieter periods in a galaxy's past. By observing the mix of stars in a galaxy, its stellar population, astronomers can reconstruct its star formation history, much like a paleontologist reconstructs the history of life from fossils. Take the Andromeda galaxy, our closest galactic neighbor, as an example. Andromeda's star formation history is a tapestry of bursts and lulls. Observations reveal that it experienced intense periods of star formation billions of years ago, followed by quieter intervals where star birth slowed. More recently, Andromeda has undergone another burst of activity, with new stars forming in its spiral arms. These cycles of star formation, bursts followed by quiescent periods, are a hallmark of galactic evolution, shaping the galaxy's structure, composition, and even its interactions with other galaxies. But why do galaxies experience these bursts and lulls? The answer lies in their environment and the forces at work within them. Bursts of star formation often occur when galaxies collide or interact, their gas clouds compressed by the gravitational forces at play. These bursts can light up a galaxy, creating dazzling displays of star birth. Over time, however, the gas needed to form new stars is depleted, either blown away by supernova explosions or consumed by supermassive black holes. This leads to quieter periods, where star formation slows or stops entirely. These cycles aren't just random, they're part of a galaxy's natural life cycle. Over billions of years, galaxies transition from vibrant, star-forming systems to quieter, more mature ones. This evolution is reflected in their stellar populations, with younger galaxies dominated by bright, blue stars and older ones glowing with the reddish light of aging stars. By studying these populations, astronomers can trace the evolution of galaxies across cosmic time, from their fiery youth to their serene old age. Star formation histories also reveal the intricate connections between galaxies and their environments. For example, galaxies in dense clusters often experience more frequent bursts of star formation due to interactions with their neighbors, while isolated galaxies may evolve more slowly, their star formation driven by internal processes. These differences highlight the diverse paths galaxies can take, each shaped by its unique circumstances. As we explore the role of star formation histories, we begin to see how these narratives are woven into the broader tapestry of cosmic evolution. From the bursts that light up a galaxy to the quieter periods that shape its future, star formation histories tell the life stories of galaxies, revealing the forces that have shaped them over billions of years. And as we continue to study these histories, we gain a deeper understanding of how galaxies and the universe itself have come to be. But what happens when we look beyond individual galaxies to explore the universe on its largest scales? How do these star formation histories connect to the broader structure of the cosmos? And what can they tell us about the ultimate fate of galaxies? That's where the story takes its next, awe-inspiring turn. Galaxies, much like living organisms, often engage in a dramatic and somewhat violent process known as galactic cannibalism. This is the cosmic equivalent of a predator-prey relationship, where larger galaxies consume smaller ones, absorbing their stars, gas, and dark matter. Over billions of years, this process has played a crucial role in shaping the universe as we see it today, contributing to the growth of some of the most massive galaxies in existence. But how does this cosmic feast unfold, and what evidence do we have to support it? One of the most striking signs of galactic cannibalism lies in the faint, luminous streams of stars that stretch across the night sky. These are tidal streams, the remnants of smaller galaxies that have been torn apart by the gravitational pull of a larger neighbor. As a dwarf galaxy is consumed, its stars are pulled into long, glowing trails that orbit the larger galaxy, like crumbs left behind after a meal. The Milky Way, for example, is surrounded by several of these streams, including the famous Sagittarius stream, which traces the remains of a dwarf galaxy that our galaxy has been devouring over billions of years. Another piece of evidence comes from the stellar halos that surround massive galaxies. These halos, composed of ancient stars and globular clusters, are often the scattered remnants of smaller galaxies that were absorbed long ago. The Milky Way's halo, for instance, contains stars that are older and chemically distinct from those in its disk, hinting at a history of galactic mergers and acquisitions. These halos are like cosmic archives, preserving the stories of galaxies that have been consumed and assimilated. Galactic cannibalism isn't just about destruction, it's also a process of creation. When a larger galaxy consumes a smaller one, it gains not only stars and gas, but also the raw materials needed for future star formation. This can lead to bursts of activity, as the influx of new material ignites the birth of stars and reshapes the galaxy's structure. Over time, these interactions contribute to the growth of massive galaxies, transforming them into the giants we see at the centers of galaxy clusters. The Milky Way itself is no stranger to this process. In addition to the Sagittarius stream, our galaxy is currently consuming the Large and Small Magellanic Clouds, two dwarf galaxies that orbit it. These interactions are slowly pulling the Magellanic Clouds apart, their stars and gas being drawn into the Milky Way's gravitational embrace. This process will continue over billions of years, eventually leaving behind only faint traces of their existence. But galactic cannibalism isn't just a one-way street. While larger galaxies grow by consuming smaller ones, the process also shapes the diversity of galaxies we observe. Smaller galaxies, though often consumed, can also influence their larger counterparts. For instance, the gas and stars they bring can trigger star formation or feed the supermassive black holes at the centers of their hosts. This interplay between creation and destruction is a key driver of galactic evolution, ensuring that the universe remains a dynamic and ever-changing place. By studying galactic cannibalism, we gain a deeper understanding of how galaxies grow and evolve over time. From the tidal streams that trace their past encounters to the stellar halos that record their history, every galaxy carries the marks of its cosmic interactions. And as we continue to explore these processes, we're reminded that the universe is a place of constant change, where even the mightiest structures are shaped by the forces of gravity and time. But what happens when we look beyond individual galaxies to explore the broader implications of galactic cannibalism? How does this process shape the large-scale structure of the universe? And what can it tell us about the origins of the cosmic web? That's where the story takes its next, fascinating turn. Galactic fountains are one of the most fascinating yet underappreciated processes in the life of a galaxy. Imagine a galaxy not as a static collection of stars and gas, but as a dynamic, breathing entity where gas is constantly being ejected into the void, only to rain back down like a cosmic waterfall. This cycle, known as a galactic fountain, plays a crucial role in shaping the galaxy's evolution, enriching its interstellar medium with the heavy elements forged in the hearts of stars. So, how do these fountains work? The process begins with the life and death of massive stars. When these stars explode as supernova, they release tremendous amounts of energy, blasting gas out of the galaxy's disk at incredible speeds. Stellar winds, the streams of particles ejected by young, massive stars, also contribute to this outflow. Together, these forces propel gas high above the galactic plane, creating vast, glowing structures known as galactic chimneys. But the story doesn't end there. Gravity, the ever-present force that binds galaxies together, eventually pulls this gas back down. As it falls, it cools and condenses, forming dense clouds that rain back onto the galactic disk. This returning gas isn't the same as when it left. It's now enriched with heavy elements like carbon, oxygen, and iron, forged in the supernova explosions and stellar winds that launched it into space. These elements, essential for the formation of new stars, planets, and even life, become part of the galaxy's chemical tapestry. The Milky Way offers a stunning example of this process in action. Observations of our galaxy reveal towering plumes of gas extending thousands of light years above and below the disk, clear evidence of an active galactic fountain. These plumes, often illuminated by the light of young stars and supernova remnants, are a testament to the dynamic nature of our cosmic home. The gas within them is rich in heavy elements, a sign of the galaxy's ongoing chemical enrichment. Galactic fountains don't just recycle gas, they also regulate the galaxy's star formation. By ejecting gas into the halo, they temporarily remove it from the disk, slowing the birth of new stars. Over time, as the gas cools and falls back, it replenishes the disk, setting the stage for future star formation. This cycle ensures that galaxies don't burn through their gas reserves too quickly, maintaining a delicate balance between creation and regulation. The impact of galactic fountains extends beyond individual galaxies. By enriching the interstellar medium with heavy elements, they contribute to the chemical evolution of the universe as a whole. These elements, once confined to the cores of stars, are dispersed across the galaxy, becoming the building blocks for future generations of stars and planets. In this way, galactic fountains are not just a local phenomenon, they're part of a larger cosmic cycle, one that connects the lives of stars to the evolution of galaxies. As we explore the role of galactic fountains, we begin to see how these processes are woven into the fabric of the universe. From the explosive energy of supernova to the gentle rain of enriched gas, they shape the life story of galaxies, ensuring their growth and evolution over billions of years. And as we look to the future, we're reminded that the cosmos is a place of constant change, where even the smallest processes can have profound and lasting effects. But what happens when we zoom out even further, beyond individual galaxies, to explore the broader implications of these cosmic cycles. How do galactic fountains contribute to the large-scale structure of the universe? And what can they tell us about the ultimate fate of galaxies? That's where the story takes its next, awe-inspiring turn. Galactic archaeology is like cosmic detective work, a way of unraveling the history of galaxies by studying their stars. Just as archaeologists dig through layers of soil to uncover ancient civilizations, astronomers sift through the light of stars to piece together a galaxy's past. Every star, with its unique composition and age, tells a part of the story, revealing clues about how galaxies formed, grew, and evolved over billions of years. This field, known as galactic archaeology, allows us to peer back in time, uncovering the secrets of the early universe through the lives of its oldest stars. At the heart of galactic archaeology is a powerful tool, stellar spectroscopy. By analyzing the light from stars, astronomers can determine their chemical makeup, temperature, and age. This is because stars act like cosmic time capsules, preserving the conditions of the universe at the time they were born. For example, stars formed in the early universe tend to contain fewer heavy elements, known as metals, because these elements hadn't yet been forged in the hearts of stars and supernovae. By studying these ancient stars, we can trace the chemical evolution of galaxies, uncovering how they transformed from simple, metal-poor systems into the complex structures we see today. One of the most remarkable places to practice galactic archaeology is right here in the Milky Way. Our galaxy is home to some of the oldest stars in the universe, many of which reside in its halo, a sparse, spherical region surrounding the galactic disk. Stars like HD 140,283, nicknamed the Methuselah star, are thought to be over 13 billion years old, making them nearly as old as the universe itself. These ancient stars are incredibly metal-poor, offering a glimpse into a time when the cosmos was young and galaxies were just beginning to take shape. But galactic archaeology isn't just about studying individual stars, it's also about understanding their populations. By mapping the distribution, motion, and composition of stars across the Milky Way, astronomers can reconstruct its history. For instance, the presence of stars with similar chemical signatures and orbits often points to a shared origin, such as a dwarf galaxy that was absorbed by the Milky Way long ago. These stellar fossils reveal the galaxy's violent past, marked by collisions and mergers that shaped its structure over time. The insights gained from galactic archaeology extend far beyond our own galaxy. By studying the oldest stars in the Milky Way, we can learn about the conditions of the early universe, a time when the first galaxies were forming and the cosmos was filled with the light of newborn stars. These ancient stars are like windows into the past, offering clues about how galaxies evolved from small, chaotic clumps of gas into the majestic spirals and ellipticals we see today. As we delve deeper into galactic archaeology, we begin to see how this field connects the past to the present, revealing the intricate processes that have shaped the universe over billions of years. From the birth of the first stars to the collisions that built galaxies like the Milky Way, galactic archaeology helps us piece together the story of cosmic evolution. It's a reminder that the universe is not just a place of beauty, but also a vast, dynamic system with a rich and complex history. By uncovering the secrets of ancient stars, galactic archaeology also raises new questions about the origins of galaxies and the forces that drive their evolution. How did the first stars and galaxies form? What role did dark matter and dark energy play in shaping the cosmos? These are the mysteries that galactic archaeology seeks to solve, guiding us toward a deeper understanding of the universe and our place within it. As we continue to explore this fascinating field, we're reminded that every star has a story to tell, a story that connects us to the cosmos and the incredible journey that has brought us to where we are today. Galaxy surveys are the backbone of modern astronomy, a vast, coordinated effort to map the universe and uncover its deepest secrets. These large-scale projects, like the Sloan Digital Sky Survey, don't just capture snapshots of the cosmos. They create detailed atlases of millions of galaxies, revealing patterns, trends, and connections that would otherwise go unnoticed. By systematically observing the night sky, these surveys allow us to piece together the story of galactic evolution, from the earliest structures in the universe to the complex systems we see today. Imagine trying to understand the history of a city by looking at just one building. Without context, it's nearly impossible, but if you have a map of the entire city, its streets, neighborhoods, and landmarks, you can start to see how everything fits together. That's what galaxy surveys do for the universe. They provide the big picture, showing us not just individual galaxies, but the vast networks and structures that connect them. One of the most groundbreaking discoveries made possible by galaxy surveys is the cosmic web, the intricate network of filaments and nodes that spans the universe. This web, composed of dark matter and gas, forms the scaffolding on which galaxies are built. Surveys like the Sloan Digital Sky Survey have mapped millions of galaxies, revealing how they cluster along these filaments, drawn together by gravity. These observations have transformed our understanding of the universe's large-scale structure, showing us that galaxies are not randomly scattered, but organized into a vast, interconnected system. But surveys do more than just map the cosmos. They also test our theories of how galaxies form and evolve. For example, the distribution of galaxies observed in surveys matches predictions made by cosmological models, supporting the idea that galaxies grow hierarchically, merging and interacting over billions of years. Surveys have also revealed the existence of red and dead galaxy systems that stopped forming stars long ago, and helped explain why. By studying these galaxies in detail, astronomers have uncovered the role of supermassive black holes and galactic winds in quenching star formation, providing key insights into the life cycle of galaxies. The power of galaxy surveys lies not just in their scale, but in their ability to capture the universe in unprecedented detail. The Sloan Digital Sky Survey, for instance, has cataloged over 3 million galaxies, measuring their distances, colors, and shapes. This wealth of data has led to countless discoveries, from the identification of rare galaxy types to the mapping of dark matter through gravitational lensing. Each observation adds another piece to the puzzle, helping us refine our understanding of galactic evolution. Looking to the future, next-generation surveys promise to revolutionize our understanding of galaxies even further. Projects like the Vera-C, Rubin Observatory's legacy survey of space and time, will map billions of galaxies, capturing the universe in motion and revealing how galaxies grow and change over time. These surveys will also explore the role of dark energy in shaping the cosmos, offering new insights into the forces that drive galactic evolution. By combining cutting-edge technology with the power of collaboration, galaxy surveys are transforming our view of the universe. They remind us that the cosmos is not just a collection of isolated objects, but a dynamic, interconnected system, shaped by the forces of gravity, dark matter, and dark energy. And as we continue to explore, we're not just uncovering the secrets of galaxies, we're rewriting the story of the universe itself. With each new survey, we're peeling back another layer of the cosmos, revealing its hidden structures and the processes that shape them. But what lies beyond the reach of our current observations? How will future surveys push the boundaries of what we know, and what mysteries might they uncover? That's where the story takes its next, thrilling turn. In the early universe, long before galaxies like the Milky Way took shape, the cosmos was a very different place. Imagine a vast, opaque sea of hydrogen gas, shrouded in darkness, where light could barely travel. This was the universe before reionization, a pivotal era that would transform it from a foggy void into the transparent, luminous expanse we see today. But what exactly triggered this dramatic shift, and how did the first galaxies and quasars play a role in this cosmic metamorphosis? The story begins just a few 100 million years after the Big Bang, when the universe was still in its infancy. At this time, the first stars and galaxies began to form, their light piercing the darkness of the early cosmos. These early galaxies were small and faint compared to today's giants, but they were incredibly energetic, filled with massive stars that burned brightly and died young. When these stars exploded as supernova, they released intense ultraviolet radiation, which began to ionize the surrounding hydrogen gas. This process, known as reionization, stripped electrons from hydrogen atoms, turning the once opaque gas into a transparent plasma. But galaxies weren't the only players in this cosmic drama. Quasars, the luminous cores of distant galaxies powered by supermassive black holes, also played a crucial role. These cosmic beacons, some of the brightest objects in the universe, emitted vast amounts of radiation, further ionizing the hydrogen gas. Together, galaxies and quasars acted like cosmic floodlights, carving out bubbles of ionized gas that gradually grew and merged, transforming the entire universe. One of the most remarkable pieces of evidence for reionization comes from observations of distant quasars. These incredibly bright objects, located billions of light-years away, provide a window into the early universe. By studying the light from these quasars, astronomers have detected the faint signatures of neutral hydrogen gas, the remnants of the pre-reionization era. These observations reveal how the universe transitioned from opaque to transparent, a process that took place over hundreds of millions of years. The impact of reionization didn't stop with transparency, it also shaped the evolution of galaxies themselves. As the universe became ionized, it created a more hospitable environment for galaxies to grow and evolve. The ionized gas allowed light to travel freely, enabling galaxies to cool and form stars more efficiently. At the same time, the intense radiation from early galaxies and quasars heated the surrounding gas, preventing it from collapsing into smaller structures. This feedback mechanism helped regulate the growth of galaxies, ensuring that they didn't form too quickly or burn out too soon. Reionization was a turning point in the history of the universe, marking the end of its dark ages and the dawn of a new era. It's a reminder that even the largest structures in the cosmos, galaxies, quasars, and the cosmic web itself are shaped by the subtle interplay of light, gas, and gravity. And as we continue to study this pivotal epoch, we gain a deeper understanding of how the universe transformed from a simple, opaque sea of gas into the complex, luminous tapestry we see today. But what happened after reionization? How did the universe continue to evolve? And what role did galaxies play in shaping the cosmos we inhabit today? That's where the story takes its next, fascinating turn. Galaxies aren't just cosmic marvels, they're also the cradles of life, The story of galactic evolution isn't just about stars and gas, it's about the conditions that make life possible. Understanding how galaxies form, grow, and change over time gives us critical insights into where and how life might arise in the universe. From the birth of planets to the availability of essential elements, the history of a galaxy shapes its potential to harbor life. At the heart of this connection is the role of heavy elements or metals in galactic evolution. These elements, carbon, oxygen, iron, and others, are forged in the hearts of stars and scattered across the cosmos by supernova explosions. Without them, planets like Earth couldn't exist. Rocky planets, in particular, rely on these metals to form their cores and surfaces. But the abundance of heavy elements isn't uniform across galaxies. It depends on their star formation history. Galaxies that have undergone multiple generations of star formation, like the Milky Way, are rich in these essential ingredients. In contrast, younger or smaller galaxies may lack the metallicity needed to form Earth-like planets. Take the Milky Way's habitable zone as an example. This region, often referred to as the Galactic Goldilocks zone, stretches between the galaxy's crowded center and its sparse outskirts. Too close to the center, and the intense radiation from supernova and supermassive black holes could sterilize any budding life. Too far out, and there might not be enough heavy elements to form planets at all. But in this middle zone, conditions are just right: enough metals to build planets, enough stability to allow life to flourish, and enough time for complex organisms to evolve. Yet, the search for life isn't just about finding the right ingredients, it's also about the environment. Galactic environments play a crucial role in fostering or hindering life. For instance, galaxies in dense clusters are more likely to experience frequent collisions and bursts of star formation, which can disrupt planetary systems or bathe them in harmful radiation. On the other hand, isolated galaxies, like the Milky Way, evolve more slowly, offering stable environments where life can develop over billions of years. But even within a galaxy, the story isn't uniform. Spiral galaxies, with their orderly arms and active star-forming regions, provide a mix of environments that could support life. Elliptical galaxies, dominated by older stars and less gas, might be less hospitable, and irregular galaxies, with their chaotic structures, could offer pockets of habitability but lack the stability needed for long-term evolution. As we explore the connection between galactic evolution and the search for life, we're reminded that the universe is a vast and varied place. From the elements that form planets to the environments that nurture them, every aspect of a galaxy's history plays a role in shaping its potential for life. And as we turn our gaze to the stars, we're not just searching for other worlds, we're uncovering the story of how life itself fits into the grand tapestry of the cosmos. This exploration leads us to an even bigger question. Could life exist beyond the Milky Way? What clues might other galaxies hold about the possibility of extraterrestrial civilizations? That's where the story takes its next, thrilling turn. As we stand on the brink of a new era in astronomy, the future of galactic evolution studies promises to be nothing short of revolutionary. With groundbreaking technologies and ambitious missions on the horizon, we're poised to uncover secrets of the cosmos that have remained hidden for billions of years. The tools will use telescopes more powerful than ever before, instruments capable of peering deeper into space and time, will transform our understanding of how galaxies form, grow, and change. And with each new discovery, we'll come closer to answering some of the most profound questions about the universe. One of the most exciting developments is the James Webb Space Telescope, already reshaping our view of the cosmos. Launched in 2021, Webb is designed to observe the universe in infrared light, allowing it to peer through cosmic dust and capture the faint glow of the earliest galaxies. Already, it has revealed galaxies that existed just a few 100 million years after the Big Bang structures, so ancient they challenge our understanding of how quickly galaxies can form. But this is just the beginning. Over the coming decades, Webb will continue to explore the universe's infancy, shedding light on how the first galaxies ignited and evolved into the diverse systems we see today. But Webb isn't alone in this cosmic quest. The Vera C. Rubin Observatory, set to begin operations in the mid-2020s, will conduct the legacy survey of space and time, mapping billions of galaxies across the universe. This monumental project will capture the cosmos in motion, revealing how galaxies grow and interact over time. By observing the universe on such a vast scale, Rubin will help us unravel the mysteries of dark matter and dark energy, two of the most elusive forces shaping galactic evolution. For instance, by mapping the distribution of galaxies and measuring their motions, Rubin will provide critical clues about the nature of dark matter, the invisible scaffolding that holds galaxies together. And then there's the Nancy Grace Roman Space Telescope, scheduled for launch in the late 2020s. Often referred to as Hubble's successor, Roman will combine a wide field of view with unprecedented sensitivity, allowing it to study the evolution of galaxies across cosmic time. One of its key missions will be to explore the role of dark energy in the universe's accelerating expansion. By observing distant supernovae and the large-scale structure of the cosmos, Roman will help us understand how dark energy has shaped the universe over billions of years, and what it means for the future of galaxies like our own. These missions are just the tip of the iceberg. Ground-based observatories, like the extremely large telescope in Chile, will complement these space-based efforts, providing detailed observations of individual galaxies and their environments. Together, these instruments will create a comprehensive picture of galactic evolution, from the first flickers of starlight to the sprawling galaxy clusters we see today. Yet, even with these advanced tools, the universe retains its mysteries. We still don't fully understand what dark matter is made of, or why dark energy is causing the universe to expand faster over time. These questions are at the heart of galactic evolution research, driving scientists to push the boundaries of what's possible. And as we continue to explore, we're reminded that the cosmos is a place of endless wonder, where every discovery leads to new questions and deeper insights. The future of galactic evolution studies isn't just about answering old questions, it's about asking new ones. What will we learn about the origins of galaxies? How will our understanding of dark matter and dark energy evolve? And what surprises lie hidden in the depths of space, waiting to be uncovered? As we embark on this new chapter of exploration, one thing is certain: the story of galaxies is far from over. This journey into the unknown is a testament to humanity's curiosity and ingenuity. It's a reminder that, even as we uncover the secrets of the cosmos, the universe will always hold more mysteries for us to explore. And as we look to the stars, we're not just studying galaxies, we're uncovering the story of our place in the universe and the forces that have shaped it since the dawn of time. As we reach the end of this cosmic journey, let's take a moment to reflect on what we've uncovered. Galaxies, those breathtaking islands of stars, gas, and dust, are far more than static collections of light in the night sky. They are dynamic, ever-changing entities, cosmic artists painting the universe with their births, collisions, and transformations. Over billions of years, They have shaped the very fabric of existence, weaving a story that is as intricate as it is awe-inspiring. From the fiery birth of the first stars in the early universe to the majestic spirals and ellipticals we see today, galactic evolution is a tale of creation, destruction, and renewal. We've seen how dark matter provides the invisible scaffolding that holds galaxies together, how supermassive black holes act as cosmic regulators, and how galactic collisions spark bursts of star formation that light up the cosmos. We've explored the delicate balance of feedback mechanisms, the role of gas and magnetic fields, and the profound influence of time and environment on galactic destiny. What makes this story so extraordinary is not just its scale, billions of years, trillions of stars, but its relevance to us. Every atom in our bodies, every element that makes up our world, was forged in the hearts of stars and scattered across the universe by supernova and galactic winds. As Carl Sagan famously said, "We are made of star stuff." We are not just observers of this cosmic dance, we are participants, living proof of the universe's ability to create complexity and beauty from simplicity and chaos. So, as you look up at the night sky, remember this: the light you see from distant galaxies has traveled across unimaginable distances and times to reach you. Each galaxy tells a story of resilience, transformation, and the unyielding force of gravity and time. And in that story, we find not just the history of the cosmos, but also a reflection of our own journey. Before we part ways, I'd love to hear your thoughts. What part of galactic evolution left you in awe? How does it make you feel to know that we're all connected to the stars? Share your reflections in the comments below. I can't wait to read them. And if you've enjoyed this exploration of the universe's mysteries, don't forget to subscribe and join me as we continue to unravel the wonders of the cosmos together. As we close this chapter, let's carry this thought with us. The universe is vast, complex, and endlessly fascinating, but it's also deeply personal. Every star, every galaxy, every atom is part of a story that began long before us and will continue long after. And in that story, we are not just fleeting observers, we are a part of the art, the science, and the wonder of it all. Until next time, keep looking up and wondering. The cosmos